Is the screen visible?
Yes, sir.
Great. So I think let's start from where we finish. So essentially, the important concepts that would be introduced in this MOSFET transistor are the following. The first one is the short channel effects. We shall talk about some of the short channel effects uh, in detail at a later stage. Then what you are having is the second order effects. I think we just started with the body effect, which is essentially due to the biasing of the substrate. And the other type of second order effect is your channel length modulation. Then we shall discuss about the types of device scaling in terms of the short channel effects that are naturally occurring in the MOSFET based transistor. Remember, we are always talking about MOSFET transistors. So as the size of the transistor or the dimensions of the transistors were scaled down, they were naturally occurring phenomena due to the physics limitations, which were velocity saturation, brain-induced barrier loading, and punch-through phenomena. So these are like the ill effects of scaling down. And the traditional MOSFET, the traditional MOSFET, which are basically also known as the planar MOSFETs, were transformed to some specialized transistors with different materials, physics, design technology, and so on and so forth. And then the basic equations that are to be remembered that one should basically should be aware of while going through this uh, introduction to VLSI design course. So as I think we have already talked about this, and we have also talked about this. So I just repeat in brief in a faster manner. So whether you are having any scaling or not, you take any transistor, any MOSFET transistor, as I told you, it is a four-terminal device. The fourth one basically is kind of neglected in most of the cases. Otherwise, if you want to play around with the threshold voltage, that means after the fabrication, uh, basically if you want the threshold voltage to be manipulated or changed, we already know what all parameters it is dependent upon while we were determining the threshold voltage per se. So those parameters could be varied when we are fabricating the MOSFET transistor in a complete circuit. So if that has passed and you have already fabricated the chip having all these transistors and still you want to change the threshold voltage, the most effective way is to have a body bias. So the phenomena basically lies to keep the source and drain junctions uh, in the reverse bias. We need to apply body voltage in the negative domain. So this decreases the impact of gauge bias and hence increases the overall threshold voltage, which is given by this. So then it becomes Vt is equal to, so basically the new Vt due to the body bias is equal to Vth plus gamma times 2 phi f plus Vsp, which is the source body voltage, minus 2 phi f, right? So this factor basically gamma is nothing but 2 epsilon q n substrate, doping of the substrate upon the oxide charge. So this is the also called as the body coefficient, and VSB is the source body potential. Please note down. Am I audible? Am I audible? No?
Yes, sir, you are.
Right. Can we move to the next slide? Can we move to the next slide?
Yes, sir.
Okay. So this is the updated version of the threshold voltage that we just defined, and this factor is actually coming due to the body bias. Now the other concept, these are the secondary concepts. So whether it's a short channel or a long channel, we will define short channel, what exactly is a short channel in at a later stage. So whether you talk of short channel or long channel, these phenomena in the MOSFET transistor actually comes into being. So the other secondary effects in your transistor configuration is the channel length modulation. So what does that mean? So as far as the digital is concerned, we talked about only two domains. The first one was linear, the other one was saturation. So the MOSFET transistor, when we talk of digital IC design or digital VLSI design, is essentially due to the fact that it works either in high state or the low state. So in the high state, so low state by it's is basically zero, right? Though it has a certain range in which it is almost called as zero. But in the high state, we basically make an assumption that there is no change, virtually no change in current with the increase in voltage. That is why it gets saturated, right? So it is also called as a constant current source. Why constant? Because even if you increase the voltage, the current gets saturated and doesn't change. So, but in reality, does the MOSFET actually acts as a current source in the saturation region? The answer is not 100% or not really. This is basically because the effective channel length. Now, this is where you are talking about the channel length. Channel length is the length in between your source and drain. So the effective channel length gets changed or gets modulated by the voltage that you applied between your drain and your source. So remember, this kind of configuration that we are taking is a N MOSFET transistor. So this is irrespective whether it's longer in length or shorter in length. And since you have a change in the effective field, that drives your pinch off basically starts to happen from here, and your channel length effectively kind of gets truncated or gets smaller in size from source to drain, from source to drain. Okay, so this basically changes the effective drain current, which is given by this parameter. ID is equal to mu n Cox W by L VGS minus VT square. Remember, this equation is valid for the transistor that is working in the saturation region. In addition to that, because of this channel length modulation, you have another factor 1 plus lambda VDS, where lambda is a channel length modulation parameter. Now, please note it down. So remember, there will be some numericals that may be based on all these things. So these are very important concepts of physics phenomena that is occurring inside the planar MOSFET transistor. We are not going beyond MOSFET transistor. So because new issues are coming due to the scaling of your transistors, which we categorize as the short channel effects, new types of geometries, new types of transistor configuration and materials are used so as to overcome the challenges which are coming due to the scaling. So this kind of transistor is valid up to say 32 nanometers. So I think the present day technology, remember nowadays, if you see all those things that are coming, though Intel were pioneers and they were doing very well, but of lately they have not been able to are you able to see? Hello? Please respond this side, otherwise I really do not
Yes,
know.
sir.
Yeah, so yeah, so though Intel it is one of the co-founders on the basis of which the scaling has been happening since the very conceptualization of the IC industry or the IT industry. That is that every 18 to 24 months, the number of transistor per unit area is getting doubled because of the scaling down of your transistors. So scaling down not only in terms of its dimensions, but also in terms of its uh, field or voltages. Okay, so even voltages have been scaled down, or so the effective field is also getting scaled down. So that has been the driving principle behind the continuous scaling of your MOSFET based transistors. But of lately, what has happened is Intel itself is not able to match up to its own postulate given by one of its own founding members, Gordon Moore. It is if we talk about the manufacturing of the IC chips, almost 80 to 90, 85 to 90% is dominated by Asian countries, including Taiwan, South Korea, and Singapore. So it is TSMC which is now talking about less than 10 nanometer as a mass scale production, not at a research level. Research level doesn't mean much until it is there on your chip which you are using in your day-to-day application. So presently Intel is lagging way behind any of the other Asian giants, including the TSMC, which is Taiwan Semiconductor. The other major fabs that are having these chips that are manufactured, in fact, almost 90% of the chips are manufactured in Asia. And remember, that's not China. It's South Korea, it's Singapore, and of course Taiwan. Taiwan is one of the biggest of all, and they are also doing well basically because they are ahead of times, even with the legendary Intel-based microprocessor. Remember, Intel is also different in terms of its architecture. Intel is basically catering to the old scheme of things. Now they have, because of the lag, they are now trying to invest more to catch up with the rest. But Intel traditionally is based on your, I think in the other course that you do, you will see it is based on your what type of architecture? Class? Are you still with me? He's sleeping. Hello? Manas?
Yes, sir.
Can you tell me?
So I think risk architecture.
No, wrong. Intel is not on risk architecture at all. Yes, Aditya Raj? Sanya? I think you must be doing in your computer architecture course. So basically, since the very beginning, there have been many architectures that are coming out. We talked in our previous microprocessor course with you guys was on 8085 and 8086. So essentially, we were talking about what type of architecture? Aditya Raj? Aditya?
Yes, sir.
What type of architecture? Mansa, what type of architecture? Sanya?
Sir, x86.
Yeah, so x86, correct. So what is that type of architecture? x86 is what type of architecture? So it is coming out of x86 series. So that is a sys type architecture. Okay, and that is why you are drawing more power. It's so what is the have you already studied about CISC and RISC architecture?
Sir, we will study in this semester only. We haven't studied yet.
Okay. The others are basically talking about RISC or ARM-based architecture. So if you see Microsoft and all, they were basically going along with Intel. That is why if you see most of these laptop or desktop that we are using, it is based on CISC architecture, and they were kind of patented, and they had their own IPs. And Microsoft came with its own operating system for such type of computer architecture. But nowadays, you have ARM, you have all these Qualcomm and the other types. They are based on the RISC or ARM type of architecture. Okay, which you use in your smartphone or tablets or even in some of the laptops. And in the future, they may even, all of them may converge to the RISC type of architecture. So even in terms of architecture, RISC is overshadowing. Again, if you talk in terms of industry, they will always try to project their one being the best. But as we have already seen, the RISC is kind of dominating the CIS. Okay, so that is in terms of its architecture. But even in terms of technology node, uh, all these Qualcomm and Broadcom and ARM, they are making their chips in Taiwan, which is having an advanced technology with respect to Intel, which is mostly done in the US. Again, they have some fab outside US. But as I understand, the latest fabs, the latest technology is still lagging far behind the TSMCs of the world. Even AMD basically gets its chip manufactured with TSMC, though they are also playing with a mixed of RISC and CIS architecture. So have you noted down this?
Yes, sir.
Okay, so we go to the next slide. So since the very beginning, we are talking about the types of scaling of a device. To fulfill the postulate or some kind of a law that was given by one of the co-founders of Intel, which was great scientist and this thing, Gordon Moore, which was to continuously improve upon the transistor so that the number of transistor almost double with respect to previous generation. So previous generation means that time would take around 18 to 24 months. So it is not a very strict rule. It generally varies because of whether the output is as desired by the, whether the output is coming, desired output is coming in time or not. So scaling of the device does not mean the reduction of channel length. It includes all the other parameters. Okay, so predominantly you are having, it all started with two types of scaling. One was the constant field scaling. Please note it down. The constant field scaling. So it yields the reduction in power delay product of the transistor, and hence it requires reduction in the power supply for the reduced feature size. Again, we will be talking probably in the next class a bit in detail about this type of scaling. So this is very important, as from time to time it is the scaling that is actually helping us to not only incorporate more number of transistors in the same chip area, but more features with reduced power. With reduced power. Otherwise, if say from 10 to 10,000 to 10 million to 10 billion, if we are able to reduce, the power shall also shoot up like anything. If we talk about, say, dimensions which were there way back in the 70s or 80s, which was which which one can say around 10 micron or 1 micron, the power to drive the circuits based on that dimension would be enormous. So one of the approaches was the constant field scaling. The other approach was to have constant voltage scaling. So this is a preferred scaling technique as it provides voltage compatibility with the other technologies. So nowadays you are having a mixed bag of both the constant field and constant voltage scaling. So remember, whenever we are going for improvement in our technology, we have to make sure that it is compatible with some of the previous generation. So like if the computer just 1 year back you came with a chip that was latest in terms of its technological parameters, those technological parameters played a very important role, say a year back or a 2 year back time gap, and suddenly you come up with new technology which is not compatible with previous generation, then you have to discard that computer or the chip that you're using. So if the computer or the chip that you're using in various type of devices is not that old, if it is not compatible, then you cannot ramp up its performance parameters. Like if you want to introduce or some more memories into the motherboard of your CPU or of your laptop or desktop or a server. So you have to make sure that at least it is compatible with last few years, maybe it's 5 years or 10 years, right? So due to this, constant voltage scaling is kind of preferred. Otherwise, and that is not only true for this, but most of the other things, whether you talk of operating system, and that is why x86 kind of had its own monopoly, because it was an extended version of the sys type of architecture was an extended version of your x86 microprocessor architecture. Due to this, electric field gets higher in smaller devices, which causes the mobility degradation and the velocity saturation. So nowadays, it is a mixed bag of two. That is constant field scaling along with constant voltage scaling. So we will just see probably in the next class a little bit in detail about this constant field and constant voltage scaling. Now, because of this constant voltage scaling, you have the ill effects, namely the mobility degradation, and the velocity saturation. So let's talk about velocity saturation. So the velocity of the charge carrier is proportional to the electric field independent of the value of the field for silicon. So Vd is equal to mu E. However, for short channel, the horizontal field gets higher and this linear relationship breaks. So we are talking about this region. Can you see the cursor? We are talking about this region. So here, as your field is increasing, the velocity basically of the charge carrier keeps on increasing. But in this region, it starts to get saturated, which is of the order of 10 to the power 5. So the velocity of the carrier gets saturated after reaching a critical electric field, which is this. So this is in the linear. Velocity of the charge carriers in the linear region and velocity of the charge in the saturation. So since E is inversely proportional to N, which is the channel length, so as you keep on, if you keep the VDS same, but you keep lowering the channel length, the electric field will keep on increasing and it will come to a stage where the field has reached the critical field value. Can we move further? Can we go to the next slide? Okay, okay. So the continuity between the two region indicates that EC is 2 times V sat upon mu. So the drain current in the resistive region, so what is resistive? Where I is inversely proportional to V. So remember, transistor, MOSFET transistor operation is a must to go into the VLSI design. ID is mu n Cox upon 1 plus VDS upon EC by ECL times W by L, VGS minus overdrive voltage times VDS minus VDS square by 2. Please note it down. So this is the equation that you see in the resistive region when you are giving the value and replacing with the onset of the critical electric field. So ID becomes this. ID is going to be from here, where kappa VDS, this term coming out, kappa VDS is going to 1 upon 1 plus VDS upon EC times L, where EC is the critical electric field. So for longer channel or a smaller VDS, kappa approaches 1. So EC, which is your critical electric field, is twice the saturation voltage over the mobility of the semiconductor device. So mu is the mobility of the silicon. That's why we call it Silicon Valley. It all starts from silicon. Now when VDS increases, then the device enters into the saturation region. So the current equation VDS gets replaced by VD sat. So this is what you should write. So ID gets can be redefined in the short channel device as kappa times VD sat UN Cox W by L overdrive times VD sat minus VD sat upon 2. So in the long channel device, which you can see here, it is at the overdrive voltage that you see your transistor getting into the saturation mode from your linear mode, neglecting the channel length modulation. While in the short channel effect, it is at the saturation voltage that you see to see your current getting saturated due to the higher field, or that is occurring due to the shortening of your channel length. Please note down, these are very important, and we will, once we start to talk how do we scale down, I will be talking in detail about that. That is very critical, because what approach, yeah, I mean, like, until unless you have another session which practically takes on scaling of your transistors, both in terms of dimension and field, keeping either voltage or field constant or a mixed package of two, you will not be able to appreciate how to improve the overall performance of your transistor by scaling of your transistors. So we talked about velocity saturation in short channel and long channel. Another important factor when we are scaling down is the drain induced barrier lowering. The drain induced barrier lowering. So if you see on the left hand side, there is a long channel device. The channel itself is long, due to which the effective electric field resulting in the barrier. What are the barrier that we are talking about? Remember, we talked about the whole, this part between source, drain and body. There is a PN or N plus P junction that is forming. And you're trying to have a kind of, if you see it on an individual basis, it is basically having different types of biases on the N plus P junction. And that is, if you talk about the whole transistor, that is related to your barrier formation. So as long as the length of the transistor is big, that means the channel length is big enough, the two types of field, effective field, one is the vertical and the other one is horizontal, does not make much of an effect. The vertical field is higher while the horizontal field is comparatively lower. But as you scale it down, then there will be changes leading to the EX and EX dominating with respect to EY as you scale down channel length L. And that would introduce the lowering of barrier. So this is what PN junction. So there is some barrier formation here in the source body region. Similarly, in the drain body region, this is also N plus P substrate. This is N MOSFET transistor. Okay, so there is, as you keep on reducing the channel length, there is This barrier is getting modulated and there is a induced lowering, barrier lowering from the drain side. So here you see like this one, 1, 2, 3. So this leads to reduction in the threshold voltage, and the transistor becoming a function of your drain source voltage. Remember, whenever you are manufacturing a transistor, if your transistor threshold voltage keep on changing with VDS, that is very detrimental. The only other way you would want is you would always want your transistors to have a fixed threshold voltage when it is operated all throughout its life, until unless you give an external bias at the body to manipulate for a particular scheme of things in a particular application. Otherwise, if it keeps on fluctuating, then all your circuits, whether you talk of combinational circuits or sequential circuits, they will create problems or would be detrimental for your functioning of the chip. So once manufactured, the threshold voltage should not change. But because of this drain-induced barrier lowering, the threshold voltage gets reduced as you increase the VDS. In other words, in long channel, when you increase the VDS, there is no change whatsoever in the threshold voltage. Even if the channel length modulation is ignored, the drain current does not get saturated due to drain induced barrier lowering. So the barrier getting lowered towards the drain side as the VDS affects the overall distribution of charges. Hello? Are you still with me?
Yes, sir.
Can we move to the next slide if you've noted it down? Can
Yes,
we
sir.
move to the okay. Another important ill effects due to the scaling of your MOSFET transistor is the punch through phenomena. If you see that between N plus P, remember in all these things, we are talking about N MOSFET transistor as an example. Same thing is also true for P MOSFET. So in N MOSFET, you have N plus source and N plus drain. And if the channel length is big enough, this depletion layer would not meet. So there will be a separation between the depletion layer between source N plus P and drain N plus P. And N plus in the source and P substrate, because this is a N plus P. If you see, it's a N plus P junction. So it will have its own depletion rate. Similarly, this N plus P will have its own depletion region. So if the channel length is big enough, there will be no meeting point. If you see, this is the meeting point. So this is happening because you are reducing the channel length. You are reducing the channel length. So when you reduce the channel length, guided by the postulate given by Gordon-Moose, and coming from using either constant voltage or constant field scaling or a mixed bag of the two, you're coming to a stage where there is an interference or there is a meeting point of the depletion region that is due to the N plus P source region and N plus P drain region. And this leads to different types of punch through phenomena. So here you can see that is happening close to the insulator semiconductor surface. The meeting point of the two depletion regions, or you can see in far away from the insulator semiconductor interface, which is far away from the interface. So this is generally referred to as surface punch through, and this is referred to the bulk punch through. So in this, the charge carriers flow directly from source to drain. Okay, because you can already see, like in the previous case, if you have a longer channel length, the depletion region between the N plus source and P body and N plus drain P body would not meet at any point. So there is no free way for charge carriers to move from, say, source to drain. So once you squeeze down the transistor based on the channel length, remember, industry defines the technology node with respect to the channel length. That is why when we say technology node, you will hear all throughout your life 1 micron, that is channel length, or 10 micron when it all started way back in the 1970, it is the channel length. Sometimes it's also called gate length, sometimes it is defined by different companies in a slightly different form. But it all is talking about the same thing, which is channel length or gate length. So in this, whether it is at the surface or in the bulk, a punch-through phenomena happens where the charge carriers flow directly from source to drain. And the slope of log of ID gets higher by decreasing the channel length. Even of the very small order. So this phenomena becomes detrimental as it does not allow the transistor to turn off even if the drain source voltage is decreased significantly. So this basically destroys the proper functioning of your transistor. In other words, it would also be detrimental for your transistor operation in digital circuits. That means all your combinational or sequential circuits that are made of these transistors would start to behave in a radical manner, and your chip will invariably is no longer reliable or gets destroyed. So whatever new physics we have talked about till now, as we will see in the future lab sessions, those physics phenomena are incorporated in the different types of EDA tools, electronic design automation tools, whether for digital or analog. So all these second order effects that influence the device performance or device analysis needs to be made simpler and tangible for analytical model so that it can be incorporated and used to give us the desired desired results for doing the analysis of a device or a digital circuit. So this model consider the MOS device as a current source. Please note down the various equations. So this you will see in the tools like the cadence or synopsis, which is used mostly in the industry. And at the back end, they have all these things incorporated. Generally, many more phenomena are incorporated in the so-called BSIM models. So we shall not get into detail, but these are very important parameters, so you please note it down. So ID is equal to 0 when your overdrive is less than equal to 0, and ID is equal to this, which also includes the channel length modulation and other phenomena, where the minimum voltage is a function of overdrive, drain source, and VDSAT. Besides being a function of voltage, the current is also a function of process dependent parameters. That means fabrication based process dependent parameters. That includes lambda, gamma, VDSAT, and VTH. Can we go to the next slide? Are you still around or you have slept?
Yes, sir.
So the body bias plays a significant role post fabrication in device analysis. So recapturing whatever we have talked about this, the miniaturization leads to several second order effects which increases the complexity of the device. Due to velocity saturation, the drain currents becomes the linear function of VGS, and well, Moore's law is still going on and will go at least to end of this decade or probably beginning of next decade. That is scaling down of your transistors. So from 10 micron, we have come to few tens of nanometer. So I think we go to the next slide, before which I will ask Mansa to show you something I just discussed with her. Mansa, just call me back. I think this before we go to the proper steps, fabrication steps, and before we go into scaling, because they are all interrelated, we have to talk about in terms of how it happens from silicon to chip. We need to know the fabrication steps. We shall talk about that. We should talk about scaling. We shall talk about the layouts. So layouts is like what, like when you're making a house, what architecture does is gives you a layout of your house. Similarly, you have the same layout when you're going for uh, chip fabrication, and there is what you call as the testing and all the other important steps, which we will be talking in detail in the overall VLSI design flow. So you need to know all these things. Yeah, so Mansa, please just go ahead. I can't hear you. Make it full screen.
Sir, is it not audible? Hello.
It's bad and it's not audible. Can someone else do it? Ishan or some of the other guys?
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch 10,000 times smaller than a human hair that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that impact nearly every facet of modern life. Intel keeps powering the world. At the same time, we're powered by you, the makers, the dreamers, the doers, the people who share in our history of making the world smarter, faster, and more connected.
Good. So did you get something, or do you have any queries? So basically, it's right now it's a very latest video. So we are talking about the new technologies as well, but the idea of giving you an exposure is like going back to the basics and then probably build up probably in your future classes if you take up VLSI as your specialization. So it is talking about using the electronic design automation tool to transistor to the fabrication to design, digital IC design to architecture, all to embedded. All these comes in the domain of VLSI systems and stuff like that. So I think we now go to the fabrication steps that are basically there to make a simple MOSFET transistor or a CMOS transistor. So what is a MOSFET transistor is what we have already defined very well. We shall also talk in detail about the different types of scaling approaches, constant field and constant voltage scaling, and the mixture of the two in our next class, in which we will be also doing some maybe one or two examples, numerical examples. So before that, we should know about the various steps that are involved. And remember, there are a lot of jobs when you are talking about not the steps, because that is what you're going to be doing in fabrication. But in India, at this moment of time, there are some fabs which are come up. But before that, you need those layout design engineers also. There are a lot of people who are into the front end and back end, using all these tools which are from either Cadence or Synopsys. So the layout, like the architectures are for houses, similarly you have it for the IC chips across the board, whether it's Qualcomm, Broadcom, Nvidia, this, that, all the companies are involved, Apple, everybody is doing this. So, and in India particularly, you are having ST, NXP, so Philips Semiconductors, or ST Microelectronics, so on and so forth, and even SCL Chandigarh, which is basically the Indian IC industry. The only difference is in the technology node. So in India, SCL Chandigarh is the moment for many years has been talking about working on mass scale production of 0.18 micrometer, which is 180 nanometer, and they are probably going into 65 or 45 nanometer. So there is a difference, but that difference is narrowing up as time is progressing. So now we go to the various fabrication steps that are involved. So can you see the slide?
No, sir.
Is it visible now? Please let me know when.
Sir, your screen sir, it is not showing that you are sharing the screen.
Is it visible now?
Yes, sir.
Okay, okay. So this is both for the fabrication steps. So remember and as well as the design rules for the layout of these transistors in a circuit. So these are very, very important and critical for you to understand. And this they will, if possible, there can be an online session as well as some practical classes. Okay, so for this, first one should be knowing that what is a CMOS. Anybody? CMOS is basically when you are talking about a N MOSFET where you are having source and drain of N plus type and body as a people P type, and bang opposite to N MOSFET transistors you have a P MOSFET. I think the way I say it sometimes is not so correct. Either one should call it N MOSFET, the other type is a P MOSFET. So MOSFET itself has transistor inside it. It is N type metal oxide semiconductor field effect transistor, and P type N MOSFET, P type metal oxide semiconductor field effect transistor. Okay, so when we have both the two together back to back, attached with some wires or connections, other type of connections, what we get is a CMOS type of transistor. And CMOS essentially is the building block of your IC industry, VLSI industry. As we know from the CMOS, we can make the so-called universal gates. Anybody? How? Anybody knows how? Banot? Banot?
Yes, sir.
Yeah. How do we make the universal gates that we have talked about, that are the building blocks for combinational circuits or sequential circuits, using CMOS? We all know what is a CMOS. I think CMOS you must have studied, or I am just trying to revise it. I hope you have studied somewhere. Yeah, Sanya, you wanted to
Yes,
say?
we have studied CMOS.
Right. So, how do we make universal gates out of CMOS? Essentially, what is a CMOS? CMOS is P-type MOSFET and NMOS, N-type MOSFET. So how do we make the universal gates? Why do we call universal gates universal gates? Because they are the building block for all the other types of gates. What are the different types of universal gates? Ishan? Kashish? Kashish? He's not there. Kashish? Arvind? Manas?
Yes,
Sir,
sir.
nor and end.
Yeah, Arvind was also saying something. Yeah, go ahead, Arvind.
Sir, nor and end are universal gates.
How about not?
Sir, not. Sir, no, sir, no. So I think node is not a universal gate.
What is CMOS?
Sir, it's a combination of PMOS and NMOS.
So, is there a difference between how do you relate CMOS with NOT gate? Ishan,
Yes, sir.
how do you relate CMOS and a NOT gate? Anybody? Is there a relation?
So they works overall same, like they inverts the input voltage, so they are same, and they both are universal gate. Like not is also a universal gate.
Correct. They are all the same. CMOS is a NOT gate. Period. CMOS is a NOT gate. And using the CMOS configuration, where you're having a PMOS and NMOS either connected in parallel or series, you get all the three different types of universal gates. So what are the universal gates? NOT, NAND, and NOR, from which probably you can make anything and everything. Even XOR, there are some different different revised version of using the PMOS and NMOS in a manner to get XOR gate. But we will not get into the detail right now, maybe at a later stage. Just a brief, because this is an introductory class. So all the universal gates are based on just combining of NMOSFET and PMOSFET in series or in parallel. So to get a simple NOT gate, that is inversion of the input by 180 degree. at the output can be achieved by placing, or by, if you talk in terms of a designer or in terms of a layout person, you're just placing P MOSFET and an N MOSFET in a series, where P MOSFET has source, drain, and the gate, and N MOSFET having source, drain, and the gate combined in such a manner that it acts as an inverter. So what are the features of P MOSFET and what are the features of N MOSFET, so that we can use it as a NOT gate or as an inverter? So if we talk about P MOSFET and N MOSFET, when does the transistor conduct should be known to us, and what kind of voltage we supply to the gate for the transistor to conduct should be known to us. Then by giving the voltage at the three terminals, remember we are at most of the times we would consider the body to be at a to be grounded or at a zero bias. So we can have the transistor operation by giving particular inputs at the three terminals that we talk about. So when we talk about a NOT gate, I think this should have been taught before. We should first know the operation of P MOSFET transistor, P MOSFET, and we should know operation of the N MOSFET. So when does P MOSFET conduct and when does N MOSFET conduct? Arvind or Kashish? Mansa? Ishan? When does P MOSFET conduct? If we need to know the fabrication steps, we should know first proper functioning of P MOSFET and N MOSFET. So when does N MOSFET conduct and when does P MOSFET conduct? Hello? Manas?
Sir, when when VGS is greater than VTH and a positive VDS is applied, then there is a drain to source current.
Can you be louder?
Sir,
Just
when
now we have talked about transistor operation. That was for N MOSFET. Bang opposite to that is for your P MOSFET. So let's start with the N MOSFET. When does the N MOSFET would conduct? Conduct basically means that the electrons are going from source to drain and the current is flowing from drain to source. Correct?
yes, sir.
Right. So go ahead.
When VGS should be greater than VTH, the threshold voltage, and there should be a positive VDS, then there is a drain to source current IT.
And how about P MOSFET?
In P MOSFET, there is a negative threshold voltage, so VGS should be more negative than the VTH, and VDS is also negative of what we have in NMOS. So in that case, there is a current from drain to source, and holes move from drain to source. Sorry,
Okay.
source to drain. Source to drain. Source to drain.
So the current would move from source to drain. Correct.
Yes.
So if you have a PMOS applied to your VDD and the drain of your PMOS is connected to the drain of your N MOSFET, and the source of the N MOSFET is connected to the ground, and you attach the gates of P MOSFET and N MOSFET to the input and the drain to the output, you get a CMOS configuration. Is that clear?
Yes, sir.
Just a moment, I just show you. So then when would your transistor work? How would the CMOS work? Yes?
Sir, when we apply a positive voltage at both the connected gate point, so a PMOS will go in cutoff region because there will be no current flow, and in NMOS, all the current will go to ground. So like output will be zero because VDS will get like output will directly connected to ground because so we'll have output zero, and when we give zero voltage at input, uh, NMOS will work in cutoff region. So the whole current will like the input voltage will go to output, and
So input voltage from where? Correct. You are partially.
from gate, like the voltage we are applying at gate.
No, no,
So,
no,
no,
no.
VDD. Yes, sir. It will get connected with the VDD, which is in PMOS, like connected through PMOS.
So what is that terminal of PMOS?
VSS, volt
That is source or drain?
source.
Source.
Yes,
So
sir.
the source in the PMOS is connected to your VDD, while the source of your NMOS is connected to your ground. And you connect the drain of PMOS and NMOSFET in a series. And the two gates is connected to the input, while the drain is the common drain of the series combination of P MOSFET and N MOSFET is connected to your output. So this is how you get what you call as the inverted output with respect to your input. So when your input is 1, the output becomes 0, and when your input is 0, the output is 1. Is that clear to everyone? This needs to be clear to everyone. The same thing also is true when you have PMOS and NMOS FET transistors connected in series or parallel to get the desired output as NOR or NAND gates. So once you know this, you can also do it for NOR and NOT gate. Anybody? Manas or Mansa or Ishan? I think Sanya has introduced you to the NOT gate using the CMOS configuration. CMOS basically means NMOS, PMOS plus NMOS. So in that, PMOS and NMOS are in series. Yes? How about NOT and NAND? Hello? Hello? I'm not getting any answer.
Sir, they are in parallel.
No. I think yes. Yes, anybody? Anybody? Yes, anybody?
Sir, actually we had an
To
idea of now.
understand, okay, you can do a reverse engineering. You know how does a PMOS work? How does a NMOS work? You know how does a NOR gate work? How does a NAND gate work? You make the table for NAND and NOR, and then accordingly design your NAND gate and NOT gate, NAND gate and NOR gate using the PMOS and NMOS transistors. Yeah, go ahead. You were saying something.
Sir, we have an idea of not gate only, sir. Um, I was saying that, sir, we'll see this, study this also.
No. I'm asking you to further your cause. Design right now.
Okay, sir.
Because you know the features of P MOSFET and you know the features of N MOSFET. When does it work and when it doesn't work? So if you know that, then you can design not only NOR and NAND, you can design anything. If you know the output, then of your NAND and NOR, you can cross verify. You don't need to study. I'm asking you to think it through because you already know the features of N MOSFET transistor as well as P MOSFET transistor.
So for NOR, we actually have the PMOS in series, and that is connected to our VDD, and to that we connect the two NMOS in parallel.
Okay, if we do that, yeah, I think you are going in the right direction. Can you just show it to us?
So,
Can
sir,
you just,
how, like, I have to draw.
yeah, just draw. And as Sanya told us about a simple inverter and its operation, you do the same thing with your design using P MOSFET and N MOSFET in series or parallel, and we already know the result. So design in such a manner that you get the desired results for NAND and NOR. To try out to make a NAND gate and NOR gate using the P MOSFET and N MOSFET in series and parallel, and see its operation and see its output. So for that you need to understand how does your inverter works. And I think when I asked Sanya, she was able to tell, and that was correct. So again, you need to understand basics. That in again, I repeat, I think it will not take more than a minute. If we have the source terminal of PMOS attached to VDD and source terminal of NMOS attached to ground, and the drain of PMOS and NMOS attached in series, as well as the drain giving the output, the common drain of PMOS and NMOS giving you the output, while the gate of PMOS and NMOS connected to the input. We would have a configuration that will be giving an output of a simple inverter. So if we give the input as 0, then P MOSFET would be in the on stage. Remember that P MOSFET would only be in the on state once it is the voltage is more than the threshold voltage. So PMOS conducts only when the inversion layer forms, while at the same stage PMOS is in the on state and NMOS is in the off state. So NMOS FET there is no conduction, while PMOS FET there is a conduction between the source and the output. That is why whatever voltage is there at VDD, it will be all going to the output, and that is how you will be able to achieve a high output. So when you are giving input as 0, your output is 1. Reverse the case, when your input is 1, then your P MOSFET transistor is in the cutoff state and your N MOSFET is in the conducting state. So whatever is at the output, as in like it is stored subcapacitor, that will be dropping to the conducting transistor here being N MOSFET, while P MOSFET is in the cutoff region, and that is connected to earth. So the output will go to state 0. So when your input is 1, then your output becomes equal to 0. The same thing will be true for your NOR and NAND gate. Remember, first of all, you make a table. What if you have A input, if you have B input, and A is 0, 0, then A is 0, B is 0, A is 0, B is 1, A is 1, B is 0, and the fourth condition would be when both A and B inputs are 1. Then you see how PMOS and NMOS can be combined in such a manner that the output is as you have already studied. I kind of presume that you already know how does your transistor and MOSFET transistor and PMOSFET transistor works, as well as what are the outputs of your NOR and NAND gate. Once you know that, you can design yourself within no time. Hello? Are you still around, or are you just moving back home?
Yes, sir.
So have you been able to do that? Tarun? Kashish? Sudhir? Sai Sudhir? I need the answer. Okay, I think you should do this as a homework so that we can move further. We will be talking about the fabrication step of MOSFET, then CMOS, then the layouts for CMOS. And
Your Honor, he is
once you
wasting God's
know
prime time.
for
I am also aware
inverter,
of Prime
CMOS basically
and
means
Netflix
inverter.
and
Once
not
you
even
know it for
downloaded one movie of
inverter,
Jackie
then you
Chan,
can
sir.
translate the
Uncle
same thing
collection of
as an
Chanakya to be investigated by the
extended
Indian
form for
Constitution, sir.
NAND gate, NOR gate, and then for any combination circuits and any kind of sequential circuits and further on. So this being an introductory class, you should be knowing your basics very well. So once you are able to do it for inverter, you can go up the ladder. Okay? I think it's
Yes,
time.
sir.
So Sanya, were you able to do it?
Yes, sir.
Okay, then tell us.
Sir, like sharing the screen is problem. Like,
Okay, good. Go ahead.
so I cannot share the screen, but can explain it.
Kindly share the screen, it would be better. Hello?
So it's
Yes.
not working. Sorry, sir.
Okay. Okay, no problem. I think I would like you to kind of do this as a homework so that we can move further. These are all very simple things, just knowing how to make a NOT gate, NOR gate, and an AND gate. These are universal gates. So for that, you should be doing at least how to make a NOT gate. Once you know NOT gate, you should be able to do NOR and NAND. Let me call off. It's 1:14. Hello. See you next Monday. Okay.
Thank you, sir.